Aren't you? Great. Cool. Okay. So, the plan for today should be to talk more about graphing and then also about optimism. And then next week on Tuesday, talk about L'Hopital's rule. And then next week on Thursday, I unfortunately have to cancel class. So sorry. I'd rather be here. I have a funeral to attend. So yeah. My plan for that missed class day though is to, I don't know what plans yet. I'm thinking about my plan for that missed day. It might just be a missed day, but I'd like to provide you with something. I just haven't gotten far enough to think about what that's going to be. So no class next Thursday, definitely class today, obviously, and Tuesday. Questions, comments, concerns? All right, let me make sure my things in order here now. And also apologies for my lateness today, just running a little behind. Today is the 6th. So we're gonna talk about graphing things because graphing stuff really kind of encompasses, in my opinion, all of the first and second derivative stuff you really need to know about. So rather than like state all the tests and kind of give formal definitions, that's something you should be getting in your actual class. Let's apply it because that's really what you're gonna have to do with it most of the time. Yeah, we might come back around to one other thing. We'll see how we feel about that. So let's look at some examples. Yeah, let's start with this one. I like this one. So let's say we want to graph. And we'll talk more about what I mean when I say graph. I know it seems like a very straightforward word, but it's got a lot of things encompassed in it. We're going to graph the function f of x equal to x squared minus 8 over x minus 2 squared. And sometimes when on an exam they ask you to graph a thing, occasionally if we feel like the derivatives are just too heinous, we'll just give them to you. So we're going to give ourselves the derivatives instead of finding them. The first derivative simplified is 16 minus 4x divided by x minus 2 cubed. And the second derivative is 8x minus 40 divided by x minus 2 to the fourth. So when I graph a function, there's kind of, well, I'll just talk about the categories to look for. So first, I typically look for intercepts. Then I usually look for asymptotes. Certainly vertical asymptotes. Sometimes we hold off on the horizontal asymptote depending on what kind of function we have. I think our next example will be a little bit more explicit as to why we might hold off. Then we're going to look for what I broadly call the first derivative stuff, meaning critical values, intervals where it's increasing or and why say things when you can write them down, James? Critical values, intervals where it's increasing or decreasing, and maxes and mins, or extrema. And then in a very, very similar way, we look for second derivative stuff, meaning critical values of the second derivative, or where the second derivative is equal to 0. Intervals where it's concave up or concave down, and then any inflection points. So when we are graphing something, these are the things I think we should be looking at. Occasionally, there's a couple other things you might consider. Symmetry occasionally comes up, like if you have an even or an odd function. Really, noticing that just makes it easier to graph. Because if you recognize that the function is even, you know that it should be symmetrical about the y-axis. So you can be like, oh yeah, the right side looks like the left side. Or if you recognize the function's odd, you can see that you have rotational symmetry. So that's not something I usually look for. I just kind of like, oh yeah, look, it happens to be this. But it's not something I'm specifically out to like test if the function's even or odd or even. So let's start. Intercepts. The y-intercept is usually pretty easy. Just set x equal to 0. And f of 0 is going to equal 0 minus 8 over 0 minus 2 squared, which is negative 8 over 4, which is negative 2. So we get 0 comma negative 2. X-intercept, a little bit harder. We're setting y equal to 0. We're setting the whole function equal to 0. So we're going to get x squared minus 8 over x minus 2 squared. Set that equal to 0. We're really just setting the numerator equal to 0. So x squared minus 8 equals 0, which means x is equal to plus or minus the square root of 8. I don't really need to know the value. I just need to know that it's a little bit less than 3. So when I graph those x-intercepts, I know they're certainly bigger than 2, and they're pretty close to the square root of 9. If you wanted a better value, you can say, well, that's going to be plus or minus 2 root 2. We know that root 2 is approximately 1.4. It's approximately plus or minus 2.8, but I don't think you even need to really know that. I would just think, yeah, it's closest to 3. Okay, for those of you walking in, we're talking about graphing functions and all the kind of things we need to do to graph a function. Next, we're going to find the asymptotes. For the vertical asymptotes, we're going to find where the denominator is equal to 0. So we're going to set x minus 2 squared equal to 0. You're going to get x equal to positive 2. We haven't really talked about this in this class, but I will point out, you don't really need to. So the thing I'm about to say, we can kind of totally ignore because you're going to get it when you do the increasing, decreasing this. But I will just point out that since our asymptote came from a factor with an even degree, that means both sides of the vertical asymptote, if they're both going to go up or both going to go down, you have the same behavior on either side. Whereas if it was odd, it would be 1 up, 1 down. But we don't need to know that because when we find the first derivative, if I were to increasing, it's either going to be decreasing on the left and increasing on the right, or increasing on the left and decreasing on the right. Got to be one of those two. And we'll see that when we do the derivative stuff. For the horizontal asymptote, broadly, the way you find the horizontal asymptote is by taking the limit as x goes to infinity or negative infinity. For a rational function, it's always the same on either side. So really just have to look at one of them. Other functions, there are some functions that have different horizontal asymptotes on the left and on the right. Kind of annoying. They're few and far between, but they do exist. Here, we would take the limit as x goes to infinity of x squared minus 8 over, I'm going to multiply out the bottom. It's x squared minus 4x plus 4. And here we can see that we have a rational function where the degree on the top and the bottom are the same. So the quotient of the leading coefficients is our limit, which is 1 over 1, which is 1. Or if we knew L'Hopital's rule, we could use L'Hopital's rule, although you don't really need to use L'Hopital's rule here. I think it's totally fair to say we know the rule for this. It's the coefficient of the highest thing or the coefficient of the highest thing if they're the same power. Great. And then the limit to negative infinity would also be 1, but I'm not going to wait. So now the first derivative stuff, which is where we actually get into the meat of things. So we're going to take our first derivative and we're going to find our critical values. To find the critical values, we're just going to set our first derivative equal to 0 / undefined. You see where it's 0, you set the top equal to 0. So to get the zeros, we're going to set 16 minus 4x equal to 0, which is going to give us x equal to 4. Define where it's undefined. We're going to set the bottom equal to 0, which is going to give us, not surprisingly, x equal to 2. We know x equal to 2 makes your derivative undefined because x equal to 2 isn't even in the domain of the function, which maybe is something we should have started with. Sometimes, I don't know. I don't think you really need to state the domain of the function, but it's not a bad idea. So it probably would have been a good idea to be like, hey, yeah, our domain is everything except for 2. So is 2 a true critical value? Absolutely not, because it's not in the domain. So x equals 2, not a true blue critical value. But it's still important. We're still going to include it on our first derivative number line and our second derivative number line so that we can tell what the behavior of the function is. Cool. Let's put all of our critical values, whether they're true critical values or not, on the number line. And nothing else. I don't want 0 on there unless it's a critical value. You don't either. You don't want anything interfering with what we're doing. Certainly in Chan's class, I think yesterday he talked about how you could figure out what's going on by determining the sign. To do that, it would have been in our best interest to factor this fully, meaning specifically, I'd like to factor out a 4 from the top. So my first derivative here, written in the best way possible, is 4 times 4 minus x all over x minus 2 cubed. So now, if I pick a number larger than 4, like 5, the top is negative, the bottom is positive, the whole thing is negative. I should say the whole derivative is negative. Whether you pick 5 or 50 or 5 million. If you pick something like 3, top is positive, bottom is positive, the whole thing's positive. Pick something like 1 or 0, the top is positive, the bottom is negative, and the negative number cubed is still negative. So it's a positive over negative, which is negative overall. So that means the function itself is decreasing left of 2, increasing right of 2, decreasing right of 4. I should say decreasing left of 2, increasing between 2 and 4, and decreasing right. I usually skip over writing the intervals of increasing, decreasing this, although there's no reason not to write them other than it takes time. So we would point out here that this function, f of x, is increasing on the interval from 2 to, excuse me, and f of x is decreasing on the interval negative infinity to 2, union 4 to infinity. And I think I've said this before, I'll say it again. Your intervals where you're increasing or decreasing or concave up or concave down should be open intervals. With, I suppose, some rare exceptions, but let's not get too into that. Lastly, for the first derivative stuff, we're going to identify any critical values. So we can see that since we are decreasing then increasing, we don't have anything there because it's undefined at 2. Don't trick yourself, right? So what I would do when I'm drawing this number line is I would either draw an open circle at 2 to remind myself you don't have anything there, or even better, draw a vertical asymptote at 2. Like, oh yeah, we got nothing there. Well, not nothing. We have a vertical asymptote, but like it's not defined there. So you cannot have a minimum or a maximum or an inflection point there. You have a vertical asymptote. It kind of supersedes any other possibility. On the other hand, over here at 4, where the function certainly is defined, we have a relative maximum. We have a relative maximum at x equal to 4. Since we're going to be graphing this, we also want to find the corresponding y coordinate. So x equals 4, y equals f of 4, which we're going to plug that back into the original function. The original function was x squared minus 8 over x minus 2 squared. So f of 4 is going to be 4 squared minus 8 over 4 minus 2 squared, which is 16 minus 8, so 8 over 2 squared, which is 4. 8 over 4 is 2. So my relative maximum occurs at the point 4, 2. You'll see shortly when we graph this that my scale for my x and y axis are not going to be at all reasonable, which is totally fine. We don't really care about getting it perfect just good enough so that someone reads like, yeah, they know what the shape of this graph looks like. All right, let's find the second derivative stuff. As a reminder, our second derivative was 8x minus 40 over x minus 2 to the fourth. And I would do myself the favor of factoring out an 8 from the top. So 8 times x minus 5 over x minus 2 to the fourth. We're setting that equal to 0. We're going to get x equal to positive 5. If we're seeing where it's undefined, we know, again, we're going to get x equal to 2. Once something's a vertical asymptote, it's going to show up in every derivative critical value kind of situation. So then we do the same thing we did before for the first derivative. We draw our number line, we put our critical points on there, and then we see if the second derivative is either positive or negative. So let's see here. Positive 2 and positive 5. Pick a number larger than 5, like 7, plug it in. 7 minus 5 is positive, 7 minus 2 is positive. The whole thing is positive. Now, if you want, you can keep picking numbers. It's totally fine. Alternatively, you can look at the place where the critical number came from, look at the factor it corresponds to, and the degree or multiplicity of that factor tells us whether you change or stay the same. If it's an odd degree, you change signs. If it's an even degree, you stay the same. Or you can test points, right? If you plug in 3, 3 minus 5 is negative, 3 minus 2 is positive, negative over positive is positive. Negative over positive is what? Negative, talking too fast. Plugging in something less than 2, like 0, 0 minus 5 is negative. 0 minus 2 is negative, but it's to the fourth power, so it turns positive. And a negative divided by a positive is what? Negative. So don't make the mistake I sometimes make when be like, okay, decreasing, decreasing, increasing. That's for the first derivative. This is for the second derivative. Second derivative tells us about concavity. So we know that at left of 2, our function is concave down. Between 2 and 5, also concave down. And after 5, concave up. We found just about everything we could. So now we're going to graph it. When graphing it, I would highly recommend looking at your sign chart for your first derivative, because that, more than anything, is going to tell you about the shape of the graph. It's decreasing, then increasing, then decreasing. That's super helpful. Before I do that, though, I'm going to plot all the things I found. Maybe all the things. Oh, I forgot something. Sorry, I forgot something. So still here at 2, sorry, for my second derivative, we have a vertical asymptote there. But at 5, since the concavity is changing, we do have an inflection point. So we have an inflection point at x equal to 5. Unlike maxes and mins, where it matters what order we change in, right? If you go positive to negative, it's a relative max. If you go negative to positive, it's a relative min. For concavity, it doesn't matter. You're just saying the concavity is changing. It doesn't matter if it's from negative to positive or from positive to negative. Either way, you'd have an inflection point. So we should find the y value. Y would be f of 5, which is 5 squared minus 8 over 5 minus 2 squared. 25 minus 8 is 17 over 3 squared is 9. So you get 17 over 9. So my inflection point is 5, 17 ninths. I would note that 17 over 9 is just a little bit less than 18 over 9, which is 2. Good question. So to be annoying, I'll say it's where the concavity changes. But to be more helpful, an inflection point looks like this. Meaning, so not the whole thing. So the inflection point is that point right there. Or if you have something cubic going the other way, about that point right there. There's a number of ways of thinking about how to find the inflection point, or what the inflection point is representative of. I'll point out, up until this point, this function is concave down, opening downwards. This function is concave up. Same deal here, except opposite. Up until that point, This function is concave up. This function is concave down. So it's where the concavity changes. Now, there's a couple extra little stupid things here. It's where the concavity changes, and also the function has to be defined, and also you have to be able to draw a tangent line. Which you might say, James, isn't that the same thing as saying the derivative exists? Well, not actually. Because I will point out that one of my least favorite functions, the cube root of x, has an inflection point at the origin. It certainly is concave up over here, opening upwards. We'll talk more about the opening upwards in a second. Concave down over here, defined at the point of inflection, and there is a tangent line there. And the tangent line is x equals 0. So the derivative doesn't have to be defined there, but you have to be able to draw a tangent line, which is, it's the definition in textbooks is always kind of wonky. All right, so a few ways to think about this. Concave down. Whenever I draw a tangent line and the function is concave down, the tangent line is always above the function. And similarly, or conversely, if the function is concave up, any tangent line is going to live below the function. And the inflection point is exactly the point where the tangent line goes through the function. Because on the left side here, the tangent line should be above the function. On the right side, the tangent line should be below the function. So it does that kind of weird. That does not look great. But that's the idea. Or over here, a similar kind of thing, right? Over here, it's below. Over here, it's above. So there's my, again, my tangent, not the best drawing I've ever seen. But if you actually graphed a graph that had an inflection point and found the tangent line like perfectly, that's how it would look. You can think of, right, like y equals x cubed, how the x-axis goes straight through it. That's also the tangent line of the origin. So inflection points have tangent lines that go through them. One other way to think about this, at least one other way, is if you think about this being like top down and you're looking like a road map, and you have like a car driving on the road, like here's my car. But really, that's a dumb way to draw it. It's in top down, not side down. So the car, as we go along the road this way, the car is turning right, 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 turning right. And then we stop turning right and we start turning left. So it's where the direction you're turning changes. One more way to say it, and then I promise to go back to the problem. It's where you have the steepest derivative. So at least like maybe starting from like, let's limit ourselves to this kind of region right here. Like right here, slightly like positive derivative, positive, negative, 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 negative. As negative as the slope gets, or as steep as the slope gets negatively, and then less negative, less negative, less negative, positive, positive, positive. So it's kind of like finding a maximum or a minimum for the first derivative. In fact, it's exactly like finding a maximum or minimum for the first derivative because you're taking the derivative of the first derivative and setting it equal to 0. That's how you find the maximum or minimum of a function. You take its derivative, set it equal to 0. Okay, I think I've said a lot of things about inflection points. Hopefully they make a little bit of sense. The way we find them, though, regardless of all things I just said here, the way you find them is you find where the second derivative is equal to 0, throw that on the number line, and then if your second derivative changes signs, either from positive to negative or negative to positive, doesn't matter which way we change, right? Whether it's this way, negative to positive, or this way, positive to negative, it's an inflection point. Okay. How do we? Oh yeah, hey, let's sure. So then we'll graph it. Whoops, come back. Yes, sorry. So now finally we're ready to graph this thing. So putting all the things I have on my graph. I have a, what do I have? Let's see, what do I have here? I have a y-intercept of -2, an x-intercept of plus or minus √8. That's terrible. I usually give myself a little bit more space between the x things often to make it easier to graph them. So there's 1, 2, 3, there's -1, -2, -3. I'm probably going to regret how much space I've used here. Oh, well. I have a vertical asymptote at +2. I know I didn't plot the things I just said. So plus or minus √8. So about like right there-ish. I don't really care about it being perfect, or about right there. And then what else do I have? I got my vertical asymptote at 2, my horizontal asymptote at 1. And then I have, what else here? Sorry. Oh, my critical points, I had a relative maximum at 4, 2, 1, 2, 3, 4, 1, 2. And I have an inflection point at 5, a little bit less than 2. Good thing that's less than 2, because that's supposed to be a maximum or a relative maximum. So it should be bigger than the stuff kind of around it. So a little bit smaller here. Okay. And now, like I said, I'm really going to refer to this sign chart to help me graph it. So I know from the left, I should be decreasing all the way until I get to this vertical asymptote here, which I should label. I also have to hit that point and that point, and if we moved leftward, we have to get closer and closer to this horizontal asymptote. So it's going to look like this. This is why it's a bad idea to plot your points first sometimes, but kind of like that. Decreasing on the interval from -3 to -2. +2. And then from 2 to 4, our function is going to be increasing, and we have to hit that x-intercept and that relative maximum. Now, when I come at that relative maximum, I don't want to come at it pointily. I want to be topping out right there so that when I go after it, I'm going on the downward trend. So I'm going to do this, increasing, hitting my x-intercept, still increasing, and then increasing until I get to my maximum. And then after that, I'm going to be decreasing. Finally, decrease. Inflection point here. Now, this is the part that's kind of a little hard to draw. I'm concave down here. I'm still turning right. And after this, I start subtly turning left so that I can flatten out and get closer and closer to this horizontal asymptote. Cool. Something that probably nobody cares about, but I'm going to point out is this graph, like many graphs, crosses its own horizontal asymptote. Totally fine to do that. Happens all the time. Right there. Could we find that point? Sure. Do we need to find it? Probably not. If you want to find it, the way you'd find it is by setting the function x² - 8 over, I'm going to multiply at the bottom, x² - 4x + 4. You set that equal to 1. And then solve for x. If you did that, you get x² - 8 equal to x² - 4x + 4. The x squareds cancel. You subtract 4 over there, you get -12 equal to -4x. So x equals +3. Nobody almost ever cares about finding that point, but I just wanted you to see that, oh yeah, a function can totally cross its horizontal asymptote, because all horizontal asymptote is saying is it's not like a barrier. It's saying that as you go way out to either side, either really, really negative or really, really positive for x, the y values get closer and closer and closer to this particular number, in this case, 1. But it doesn't say anything about what's happening in the middle. In the middle, all sorts of crazy things can happen. You can cross that horizontal asymptote as many times as you want. So it's kind of a long process, but that is the process, at least as far as I'm concerned, for graphing a function. Intercepts, asymptotes, first derivative stuff, second derivative stuff, graph the whole thing. Yeah. I know it's kind of first derivative stuff and second derivative stuff are 3-word phrases that are doing a lot of heavy lifting there, right? First derivative stuff, find the derivative, set it equal to 0, find your critical points, put them on the number line, see if you got a max or a min, increasing, decreasing, all that jazz. Same thing for the second derivative. That's a very blanket statement about the process. Questions, comments? about this before we do more examples. All right. We'll do a couple more examples. And then we should start talking about optimization. All right, let's do this next example, which is going to be a little bit different. I mean, they're all going to be different, but so let's say our function that we're going to graph is going to be f of x equal to x squared times the square root of 12 minus 2x squared. And unlike the previous problem where it was obvious, relatively obvious, that the only domain issue was that x couldn't equal 2, and we got a vertical asymptote there. This function with this square root here does have a fairly restrictive domain. So it probably is worthwhile to actually start by considering the domain. So let's start with the domain. The domain is going to be that the inside of the square root had better be non-negative. Normally, I would say you should factor something like this, but since you've only got an x squared term and a constant term, you can solve this just by bringing, I really would prefer to factor it, but no, I'll do it the other way, fine. 12 bigger than or equal to 2x squared, 6 bigger than or equal to x squared, which means x has to, well, I will square root both sides. Square root of 6 bigger than or equal to the square root of x squared. And what's the square root of x squared? Not just x, absolute value of x. So if the absolute value of x is less than 5, I know that's not 5, then x is between 5 and negative 5. So if the absolute value of x is less than or equal to root 6, that means x is between root 6 and negative root 6. So that's our domain. We're actually pretty limited here. Like as far left is 2 point something, and as far, or sorry, negative 2 point something, as far right is positive 2 point something. Okay, so keep that in mind as we start graphing here. But now we're going to do the usual things. We're going to find the intercepts. Y-intercept, f of 0 is 0 times the square root of 12, which is 0. So 0, 0 is our y-intercept. It's also an x-intercept. X-intercepts, usual deal, set the whole thing equal to 0. When you've got something factored like this, you're just going to set each factor equal to 0. We already know that this factor is going to give us x equal to 0. Setting 12 minus 2x squared equal to 0. It'd be probably smart to utilize some of the work we already did. It seems like when we set this to be greater than or equal to 0, we end up getting x between root 6 and negative root 6. Setting this equal to 0 should end up yielding x equal to root 6 and negative root 6. You can plug it in and check, right? Root 6 squared is 6. 2 times 6 is 12. 12 minus 12 is 0. Same thing is true for negative root 6. So we're going to end up getting x equal to plus or minus root 6. So we have 3x intercepts, root 6 comma 0, negative root 6 comma 0, and 0, 0. All right. The first derivative stuff is going to be a little bit gnarly. I would certainly be imagining this as x squared times this quantity raised to the 1/2 power. So my function is x squared times 12 minus 2x squared to the 1/2. And to take the derivative, we're going to have to use the product rule. It's going to be 2x times the other stuff plus x squared times the derivative of this stuff, which is going to be 1/2 times our quantity, the negative 1/2, times the derivative of the inside, which is 0 minus 4x. And then we're going to set that equal to 0. Ugh. How do I like to think about this? So a couple ways to go here. I personally would recommend factoring out. If you prefer, you can write that. You could also think about writing as a common denominator. So I'll do it the second way actually here, just to kind of point out that you can kind of go either way. So I'm going to write this as 2x times 12 minus 2x squared to the 1/2. I'm going to leave myself some space next to it, plus I'm going to rewrite this as -4 divided by 2 is -2. X times x squared is x cubed. Instead of writing it as 12 minus 2x squared to the -1/2, I'm going to write it over 12 minus 2x squared to the +1/2. And then I'd really like to have a common denominator. So I'm going to multiply this piece over here by 12 minus 2x squared to the +1/2 over the same thing. Simplify. Still we're saying equal to 0, but whatever. So now we have a common denominator. So I have the following. I have 2x times this times this, 12 minus 2x squared to the 1/2 times 12 minus 2x squared to the 1/2 is 12 minus 2x squared minus 2x cubed, all divided by 12 minus 2x to the 1/2 power. And now it's a little easier to factor stuff out from the numerator. I think we can see that both from this piece and from this piece, I can factor out a 2x. And that means I'm going to have 2x times a 12 minus 2x squared here and a negative x squared over there. And since I'm running out of room, I'm not going to, I should simplify. That's lazy, James. Fine. So 2x times 12 minus 2x squared minus x squared is 12 minus 3x squared, all over the same thing. Factor the top as much as possible, and you factor out a 3. And then you have a 4 minus x squared, which factors as 6x times 2 minus x times 2 plus x. Goodness, lots of work to do. That's why sometimes they give you the derivative, because look at how terrible all that work is. Finally, setting that equal to 0 or undefined, we see that we get critical points x equal to 0, +2, -2, and then also the things that make the denominator 0, which are plus or minus √6. But plus or minus √6 is the end of our domain. So we'll check that out when we draw the number line in a second here. Yeah.
So why did you, or where did the times 12 minus 2x to the 1/2 over 12 minus?
So I had a thing that I was adding to a fraction. And to be able to deal with that reasonably, I really needed a common denominator. That's why I multiply by the top and bottom by this denominator, so that this expression, which is some fraction divided by 1, would have the same denominator as that expression. So I can have them together. I will point out alternatively, and probably the way I'd prefer to do this, is you could also approach this situation by just factoring from the get-go. Instead of getting a common denominator, again, you don't need to do it this way, but if you wanted to, we could have said, oh, look, from each of these pieces, I can factor out a 2x. And from each of these pieces, I can factor out a 12 minus x squared to the -1/2. From the first piece, the 2x is gone, but I factored out a 12 minus x squared to the -1/2, so I'm left with a 12 minus x squared to the +1. Because if you multiply that by that, you add the powers and you get +1/2. Similarly, from over here, I factored out a 2x, which is this piece right here, the 1/2 times 4x. I'm left, oh, and I also factored out the 12 minus x squared to the -1/2. So I'm left with a x squared times the -1. Rather two things, sorry. And if we simplify this, it's 2x times 12 minus x squared to the -1/2 times 12 minus 2 minus 1 is 12 minus 3x squared. And this exactly factors in the same way. It's 2x times 12 minus x squared to the -1/2 times 3 times 4 minus x squared, which is 2 minus x times 2 plus x. That is exactly the same as what we've written right here. It looks a little bit different. I would do it this way personally. But some people, I feel like some people don't love factoring out the thing to a negative power. So that's why I showed both those. Okay, now we're going to use the number line for our first derivative. And I've kind of done it wrong here. I shouldn't really have arrows at the end because I'm not going to infinity. I'm stopping at negative root 6, and positive root 6. This function isn't defined to the left or right of those numbers. And then my other critical values are, what were they? 0, 2, and negative 2? Yep. 0, 2, and negative 2. Gross. So this is where we have to be, I think, kind of extra careful. Here's our expression. Something to recognize. This quantity right here is never going to change signs. Whatever you plug in for x, that's between negative root 6 and root 6, like 2 or 1 or 0, that number squared is always going to be smaller than 12, and 12 minus it's always going to be positive. Yeah, for sure. Did I forget my 2 again? I sure did. Wow. Wow. Really good job, James. Really excellent here. Sorry about that. In each of these instances, I forgot the 2 that was here, the 2 that was here, the 2 that was here. Sorry about that. So, but still, my comment stands. If you plug in the number like 2 squared is 4, 2 times 4 is 8, 12 minus 8 is still positive. Because this quantity has to be positive because that was a requirement for the domain in the first place. So I'm never even looking at this when I'm thinking about the sign of my first derivative. So pick a number bigger than 2, like 2.1, because root 6 is not that much bigger. Positive, always positive. Negative, positive. I had one negative, the whole thing's negative over here. Between 0 and 2, pick one. Positive, 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 positive. Pick negative 1. Or look at the power of x to the first. Oh, it's a 1, it's going to change signs. We pick negative 1. Negative, positive, positive, positive. Finally, negative 2.1, negative, positive, positive, negative. I said negative twice. So we have our function increasing, decreasing, increasing, decreasing. How many critical points do I have? That's a bad question. How many extrema do I have? Put on your fingers. It is 3. How many of them are relative minima? Yep, a relative minimum at x equal to 0. And it's funny when you say one thing and you write. The problem was my brain was always like, and you're going to say y equals this. And I wrote that before I said it. X equals 0. And we already know the y value is our y-intercept, which is also 0. Similarly, relative maxima at both x equal to 2 and x equal to negative 2. For x equal to 2, our y is going to be f of 2. Yep, thank you. Plugging back into our original function, which was x squared times the square root of 12 minus 2x squared, we're going to get 2 squared times the square root of 12 minus 8, which is 4 times the square root of 4, which is 8. And for negative 2, f of negative 2 is going to be negative 2 squared times the square root of 12 minus 8, which is also going to be 4 times 2, which is 8. All right. Looked like a fairly innocuous function. Seems like it's gotten pretty terrible. So, lastly, I think we don't even want to find the inflection points here. Yeah, I really don't want to. Doesn't mean we shouldn't. So let's take a look. Let's take a look though at our first derivative. Remembering that our first derivative was simplified. It was this thing here, 2x times 12 minus 2x squared, the negative 1/2. I'm gonna sneeze. Or not. Times 3 times 2 minus x times 2 plus x. Yeah, that seems really terrible. Let's graph it first, and then maybe we'll talk about our inflection points if it seems relevant here. So here's our graph. Our domain is everything from negative root 6 to positive root 6. And then at -2, we have a maximum. At 0, we have a minimum. At +2, we also have a maximum. And at root 6 is the end. So our graph kind of does something weird. I mean, a lot of graphs are weird. Yes, of course, always, sorry. So it should have a little more symmetry than I've drawn it with. A couple things to note here. I skipped something earlier. I skipped talking about vertical asymptotes and horizontal asymptotes because there weren't any. We knew there weren't any vertical asymptotes because the function didn't have any division by 0. And we knew there weren't any horizontal asymptotes because our domain was limited, right? We couldn't go further than root 6 to the right or negative root 6 to the left. So we didn't even have to think about those things. And while one could find inflection points, there's probably an inflection point like right there and right there. I don't think that's the best use of one. I think they'd be terrible to find. So let's not. If you really want to find them, come talk to me later. But it's not a good question. It's a yeah. Let's look at another example. One more example, and then we should start talking about optimization. So let's look at the following. Let's graph f of x equal to x times e to the x. Okay, so this one much less terrible. Usual things. Also point out, no domain issues here. No roots, no radicals, no logarithms. I know roots and radicals are the same thing. And no division by 0. So we're good. So, y-intercept. F of 0 is 0. X-intercepts. X e to the x equal to 0 is going to yield just x equal to 0. It's a really important reminder that e to the x is never 0. E to the anything is always positive. So if you were to set each factor equal to 0, setting e to the x equal to 0 doesn't get you. Vertical asymptotes, there aren't any. We don't have any division by 0. I should point out, in addition to division by 0, logarithmic functions can also have vertical asymptotes. So when you have a natural log of x, or log based on anything, but usually natural log, you need to consider what's happening as x gets closer and closer to 0, or whatever makes the argument of the logarithm 0. Usually, it's going to involve L'Hopital's rule, to be perfectly honest. Like later on, if you were to graph something like x times natural log of x, no, that's not necessarily true. So a great example of where that statement isn't true would be the function, the cube root of x. So the cube root of x, definitely defined everywhere, doesn't have any asymptotes at all, but definitely has a vertical tangent line at the origin. Yeah. I know, I'm trying to think about, like I think I saw the thing he was talking about in class that you were kind of alluding to. Yeah. So what I would say very kind of broadly is you look for vertical asymptotes first with the original function, and then we either have them or we don't. And I would say that vertical tangent lines are kind of a whole separate animal. Like sometimes we get them, sometimes we don't. But we only really ever get them when the derivative is undefined. In fact, let me write this down. So I would say kind of generally, we only get vertical asymptotes at places where the function itself is defined. You can't get a tangent line at a place where the function doesn't have a point, but the derivative is undefined, right? Because to have a vertical tangent line, The slope of the tangent line has to be undefined, which means the derivative is undefined. And again, a great example is f of x equal to x to the 1/3. And the point is 0, 0. A non-example would be f of x equal to x to the 2/3. One of my favorites, what I call the bird function. Defined everywhere. Derivative is undefined at 0. We do not have a tangent line at 0 at all because we have a pointy point, right? You don't get a tangent line if the function isn't smooth. So when you have pointy points, cusps, corners, no tangent lines. Whereas with f of x equals x to the 1/3, which I should let myself room to draw here, sorry. This function is smooth. It just goes vertical for a split second there. So that one definitely has a vertical tangent line, x equals 0. That one definitely does not have a vertical tangent line because the slopes from the left are super negative and the slopes from the right are super positive. Cool. Back to this question. No vertical asymptotes. Horizontal asymptotes. This is the place where if you don't yet have L'Hopital's rule, we're going to leave it for later. Because although the limit as x approaches infinity of x e to the x is just infinity times e to the infinity, which is infinity. The limit as x approaches negative infinity is a big negative number times a very small number. E to a negative infinity is like the left side of the e to the x function, which gets closer and closer to 0. So this is, I really don't like writing infinity times 0 because that's confusing to people. People think, oh, anything times 0 is 0. We don't really have infinity times 0 or negative infinity times 0. We have a big number, a negatively big number, times a small number. Which one wins? Good question. We don't know without L'Hopital's rule, but we can get away without using it using some graphical methods and also some common sense in a second here. But we'll leave that for a minute. So this one here, we'll come back to that. First derivative stuff. First derivative is using the product rule. It's going to be 1 times e to the x plus x times e to the x. We definitely want to factor out the e to the x, set the whole thing equal to 0, and get x equal to -1 as our only critical value. Number line, only -1 goes on there. Pick something larger than -1, like 0. E to the 0 is positive. 1 plus 0 is positive. E to the anything is positive every time. Pick something less than -1, like -5. E to the -5 is positive. 1 plus -5 is negative. So positive is negative. So our function is decreasing then increasing. So we have a relative minimum at x equal to -1. The corresponding y value is f of -1, which is -1 times e to the -1, or -1 over e. Let's find the second derivative stuff. So second derivative, you could use either version. I often generally don't like the factored form for my next derivative. This one's probably not so bad though. So I'd probably just use that. So my derivative here is going to be the derivative of e to the x times the other stuff plus e to the x times the derivative of the other stuff, which is 1. Factoring out the e to the x, we're going to get 1 plus x plus 1, which is e to the x times x plus 2. Set that equal to 0, you get x equal to -2. Notice I'm not even bothering to say set it equal to 0 or see where it's undefined, because we know that this expression is never undefined. We don't have any of the typical undefined things or things that are undefined in certain places. Throw this on your number line. Pick a number larger than -2, like 0, positive, positive. Less than -2, like -3. E to the -3 is still positive. -3 plus 2 is negative. So our function is concave down, concave up. I don't think I'm going to write the intervals where it's concave up. I think you can write the intervals, right? It's increasing from -3 to -1. Sorry, it's decreasing from -3 to -1, increasing from -1 to infinity. Concave down, -3 to -2. Concave up, -2 to infinity. Let's try to graph. So on my graph, I have my intercept of 0, 0. I have my relative minimum of -1, comma, -1 over e. I'm going to draw the y-axis, like a little too big here. So -1 over e is about -0.3. 1 over e is about 0.3. It's not perfect, but close. But I don't really care. There's my minimum. And then also at, oh, I didn't find the y value for x equals -2. Sorry, plugging x equals -2 back into the original function, x e to the negative x, y is going to equal -2 e to the -2, which is -2 over e squared. E squared is pretty close to 8. So -2 over e squared is pretty close to -1/4. And not surprisingly, it should be a little higher up than my minimum. Okay. Also worth noting, this graph has how many x-intercepts? 1. Meaning there's only one place, the origin, where we can cross the x-axis. If we even cross it there, we might bounce off. We don't bounce off, but okay. Meaning that there's no other places to cross the x-axis. So that's going to help us find the horizontal asymptote, if there is one, which there is. So looking at my increasing, decreasing, cool. So from the left, I'm decreasing, and I kind of don't have a choice. I can't go above this or this axis here, right? Because I don't have any other x-intercepts. So I kind of have to look like this. I'm concave down over here, and then I switch. Instead of turning to the right, now I start turning to the left. Bottom out, keep turning left, hit the intercept, keep turning left. Concave down, concave up, decreasing, increasing. And we have to, we're kind of forced to have a horizontal asymptote of y equals 0 to the left. You can say y equals 0 as x goes to -3, although you don't really need to say that. Back to how we could have determined that without using L'Hopital's rule. Well, if you look at the limit as x goes to -infinity of x times e to the x. I usually like to have, what do I like to have? I don't know. I like to have a fraction where both things are getting big, if that's a possible way of writing. It's not always possible, but it is here. I would much rather write this as the limit as x goes to -infinity of x over e to the -x. So on top, we have something that's getting negatively infinitely large. On the bottom, we have something that's getting positively infinitely large, because you have e to the negative infinity, which is e to the infinity. Okay, let me ask you all a question. Which function grows bigger? E to the x, I should say, y equals e to the x or y equals x? Right, e to the x by miles, right? E to the x is so much bigger than x, right? You plug in like 5, e to the 5 is, I don't know, on the order of 200 or 5, right? One of them is clearly outpacing the other one. So if your fraction is such that the denominator is much, much, much larger than the numerator, that fraction is getting smaller. It's getting closer and closer to 0. Now, just so that we can prime the pump for L'Hopital's rule, the way L'Hopital's rule works, if you haven't heard of it, or if you have, is that if you have a limit that's indeterminate, specifically of a 0 over 0 form, or an infinity over infinity form, doesn't matter if they're negative or positive or one of each, you can use L'Hopital's rule, which says you can find the limit by taking the limit of the derivative of the top divided by the derivative of the bottom. And then if you let x go to -infinity, e to the negative infinity is e to the infinity, which is super big. And 1 divided by an infinitely large number is infinitesimally small. So that's very, very broadly the idea for L'Hopital's rule. I will remind you heavily to use L'Hopital's rule You can only use it in two situations. If your limit looks like a 0 over 0 or some sort of infinity over some sort of infinity. I will remind you, we didn't start with that. We started with this, which is not either of those things. So if you have something that's indeterminate, like a really big number times a really small number, which people say is an infinity times 0, before you can correctly apply L'Hopital's rule, you have to manipulate the expression so that it's a fraction, has to be a fraction, must be a fraction. Does it need to be a fraction? Yes, it does. And it has to be 0 over 0 or infinity over infinity, some plus or minus whatever. So make sure that if you're thinking about using L'Hopital's rule, first of all, it's a limit, right? It's only for limits, it's not for anything else. And you're making sure that limit is of a fraction, and that fraction, the top thing's going to 0 and the bottom thing's going to 0, or the top thing's going to infinity and the bottom thing's going to, which we'll talk more about on Tuesday. Okay, so I'm always never leaving myself enough time to do all the things. Maybe if I got here on time, that would help. I feel bad about being late. Usually I'm more on time. Let's go ahead and talk about optimization for the last 15 minutes of class here. And more on, so that's what Thursday will be, is optimization and L'Hopital's Tuesday. So optimization. Let's look at the following situation. We want to construct an open top box. Let me see one thing here. I want to check one thing. Yeah, sure. Yeah. Using 250 square inches of material. We also want the box to have a square base. What dimensions of the box will maximize the volume that it holds? Usually for an optimization question, I like to start by drawing a picture of the thing. So we're trying to construct an open top box. So it's three-dimensional. Here is a couple of silly ways of doing it. I could draw a box that had dimensions like this, that was super tall, and maybe had, I don't know, a 2-inch base and my brain has left me, I apologize. And a height of, I don't know, 200. Sorry, this is what happens if you don't do math. A height of 123, about 246 divided by 8, whatever that is. Because if you multiply all those numbers together, the surface area would be 250. Let's check and see. My base is 2 times 2, and my side areas are going to be 2 times 246 over 8, plus another one of those, another one of those. Oh, there's 4 of them. Oh yeah, that's going to be 246 plus 4, that's going to be 250. Is that box going to maximize the volume? No! That box has very little volume for that amount of surface area, right? I made like the skinniest, tallest box I could think of. I guess it could have been skinnier, right? But you get the idea. Or you can make a really flat box with a square base, where maybe the height is like 1 inch. And the base is, I don't know, I didn't do the math ahead of time. So the base is something like, well, sorry, my brain is not on fire today. It's about going to be, I don't know, the square root of something. It's going to be small, the volume. Sorry, I made up different numbers to make the problem slightly more interesting, and I'm regretting it immediately. Anyway, the volume here would be whatever this dimension is times whatever that is, which is again not going to be very much. X squared times 1, and x is probably something on the order of like 15. 15 times 15 is 220. Yeah, that seems about right. Probably x is about 14 or 15. So 220 square inches, cubic inches of volume, not a lot. So here's what we really want to do. We'll say, well, we don't know the dimensions. So we're going to draw a picture of our box and try to figure out what values of x and y. Again, labeling my base square as x times x and my height as y so that we can maximize the volume. So we want to maximize the volume, which in this case would be equal to x times y, or x squared times y. Now, as you might have experienced already, we can maximize functions. We know how to find the maximum of a function, but all the functions we maximize are functions of one variable. And this expression that we want to maximize has two variables. That's a problem. This is where we need to pull in the other piece of information, which is that we are constrained, right? We have a limiting amount of material to use, or more generally, there's always some limiting piece of information that's saying you only have this much stuff, or you only have this much distance, or something that you have a limited supply of. So in this case, our constraint is that we want to make it so that we're only using exactly 250 square inches of material. Or in other words, the surface area of this open top box, what is open top, James? Of this open top box should be 250 square inches. So the surface area, which the equation for is the area of the bottom, plus the area of the four sides. The front is x times y, the back is x times y, the right is x times y, the left is x times y. It's 4x times y. If it was a closed top box, it would be 2x squared plus 4xy, but we don't have a top, so we don't have surface area for that. We want that to equal 250. So almost always your constraint equation should be equal to some number, or occasionally your teacher will say like something like the surface area is a constant, and then you'll set it equal to c, which is more annoying, but often what people like to do. And then you'll work it that way. Whereas the thing you're trying to optimize isn't equal to a number. We don't know what the volume is. We're trying to maximize it. So then after you've identified those two things, the process is pretty not straightforward, but the steps are the same every time. You typically solve the constraint for one of your two variables and plug that into the other equation. You almost always have a choice, and sometimes it doesn't really matter. Sometimes it really matters. In this case, it is much, much easier to isolate y. Isolating x, you have to pull out the quadratic formula. We don't want to do that. So pick the easier variable to isolate. So for x squared plus 4xy equal to 250, isolating y, we have 4xy equal to 250 minus x squared, and then y is equal to 250 minus x squared, all divided by 4x. Normally I'd simplify, but let's wait because we're going to plug this into the other equation and see what happens. So now our volume equation, which was x squared times y, we're going to plug this expression in for y, and we're going to get that our volume now as a function of just x is equal to x squared times 240 minus x squared all over 4 times x. How did my 5 turn into a 4? I don't know. Magic of making mistakes. Sorry, 250 divided by 4. And then the reason I didn't divide that through is because we can cancel an x in the denominator with one of those x's there. And then I would choose to rewrite this in the following way before I differentiate. The divided by 4, let's put that out in front as a 1/4. And the x times 250 minus x squared, let's distribute that and get 250x minus x cubed. Okay. Now we're gonna take the derivative, so it's equal to 0, find the point. So v prime is 1/4 times 250 minus 3x squared. All right, so I really thought I know. Oh well, sorry. I was trying to make the numbers nice. I made them worse accidentally because I multiplied the wrong two numbers in my head together. Such is life. We can still do, I mean, that doesn't mean we can't solve the problem. This means the numbers aren't going to be very nice. That happens. So set this equal to 0, solve for x. We have 250 minus 3x squared equal to 0. We have 250 equal to 3x squared. 250 divided by 3 equals x squared. So we get x equal to plus or minus. What does x represent? The length of the side of the box. We probably should just limit ourselves to the values that make sense. So here we're going to say that x is the positive square root of 250 divided by 3. And then, looking at our equation for y, we're going to take our x value and say, okay, y is equal to 250 minus the square root of 250 over 3 squared divided by 4 times the square root of 250 over 3. Which is not very pretty, but it is an answer. It could be simplified a little bit. Yeah, there is a reason to simplify this. So I am going to simplify it. Check out what happens. We get 250 minus 250 thirds over 4 times the square root of 250 thirds. I do want to simplify this for you so you can see the relationship here. So when you have a thing minus a third of a thing, what are you left with? 2/3 of the thing, right? Something minus a third of itself is 2/3 of itself. So on top, we have 2/3 of 250. Thank you. On the bottom, we have, sure, 4 times the square root of 250 thirds. And what I really wanted to write this as was, 2 times 250 over 3 over 4 times the square root of 250 over 3. Because something divided by its own square root is equal to its own square root. And we end up getting 1/2 of the square root of 250 over 3. So kind of interestingly, the y dimension is exactly half of the x dimension. That's pretty typical. Apologies for the gross numbers. I did not mean for them to turn out quite so ugly. So our solution here is that the dimensions are x equal to the square root of 250 over 3, and y is equal to half of that. Lastly, and this is kind of something we can't ignore, we wanted to maximize the volume, but all we did was find the critical value. Do we actually know that it maximized the volume? So here's what I would say. Usually when you're asked this question, the thing you're going to find is the thing you're hoping to find. Like if they ask you to find the thing that minimizes the thing and you find one critical value, it's going to minimize the thing. If they're asking you to find the thing that maximizes something and you find one critical value, it's going to maximize the thing. The way you could check this is by using the second derivative test. So we can say, cool, if we look at the second derivative, v double prime, so there's where'd my first derivative go? Right there. My second derivative is going to be 1/4 times negative 6x. And no matter what positive number I plug in for x, in this case, my critical value, v double prime of the square root of 250 over 3, I'm going to plug that in and it's going to be negative. And if your second derivative is negative, which way is your concavity? That's concave up. Concave down. And if it's concave down, that means you have a maximum. That's what the second derivative test I think is actually useful for. When you're optimizing and you're like, well, I don't really want to test this critical point in some other way, like using the first derivative test, which is just kind of super annoying, and you have to worry about the domain. You can instead just say, as long as the second derivative isn't terrible, use the second derivative test. Take the second derivative, plug in your critical point, and if it's negative, you have a max. If it's positive, you have a minimum. So yes, it is a maximum. All right, that's all I got. 2:30. Tuesday, we'll continue talking about optimization with some problems that have less terrible numbers. Sorry again. And as I mentioned earlier, we will not have class on Thursday. I'll try to figure out some sort of content for you, help you review for your finals. What day are your finals on? Tuesday for some people, and another day for some other people. I think it's on campus somewhere, but yes. So that's what you have to look forward to. I have a funeral to go to.
Oh.
Yeah, no, I would much rather we had class on Thursday, but unfortunately, I need to be out of town. No, it's really okay. I said it to everyone earlier. It's fine. You're asking. I'm not. It's really, yeah.
No, we have Thursday.
What's that?
No, it's class final Thursday.
Okay, cool. And then also I should mention I'll post on campus as well. Actually, two things. Thing one, there is or will be shortly an evaluation at the very top of the modules in Canvas. Please fill it out when you have a chance. Just giving me like your opinions about the class, things I can do better and stuff like that. And then more importantly, yeah. Next, the week of finals. The week of finals, there will be office hours and they'll all be in the math drop-in area in the library. So during finals week, if you're looking for help, you can come find me or Grant or Ryan or Jen or any of the math tutors in math drop-in in the library. And we're pretty much there from, I think, 11 to 4, Monday through Thursday. I'll say it again and I'll post it. Just thought to mention it. Think about it. Yeah.
I think one question. So
Yes.
how did these become 1/2 of just the thing, or did I copy it wrong?
No, you were right. Because 2 divided by 4 is what?
1/2, but what about like
So when you take a thing, let me ask you a question. What's the square root of 9?
3?
What's 9 divided by the square root of 9?
9/3, which is 3/1.
Which is 3, right?
Uh-huh.
Or as I would say, 9 divided by the square root of 9 is the square root of 9.
Oh, okay, so it's 1. Oh, okay.
So anything divided by the square root of itself is equal to the square root of itself.
Oh, okay.
So that's kind of the trick I was employing.
Okay. And one quick example. In this example from here, like, is -2 like where the concavity